Right, so let's do a problem here. From here on out, we'll do some problems involving colligative properties. All right, so on an exam, there'll be a short answer question, and the short answer question is this: what are the 4 colligative properties? Can you guys name me one? What happens if you make a solution, which is solute solvent? What 4 things happen?
The boiling point elevates.
The boiling point goes up. You'll get a new boiling point, which is higher. And what happens to the freezing point?
Goes down.
We'll have a new freezing point, which goes down. What happens to the vapor pressure? Okay, we'll have a new vapor pressure, but will it go up or down? So you add a solute to a solvent, there's more IMF, more solute-solvent, solute-solute interactions to overcome to become a vapor. So will it go up or down? Okay, so it's going to go down. It will be harder to become a vapor. Okay. Why will it be harder to become a vapor? Because there's more IMF, right? If you have a solute with a solvent to make a solution, you'll have more IMFs to overcome. And then finally, we have osmotic pressure that's generated. Right, so we'll do some problems involving these 4 colligative properties. Right, the first problem that we will do is a vapor pressure problem. Yes, vapor pressure. Okay. So I'll give you this equation on the exam, so you do not have to memorize it. The new vapor pressure of the solution, okay, once you add a solute and a solvent, is going to be the mole fraction of the solvent, okay, times the solvent by itself. Okay, this is also called neat, which means solvent totally by itself. Neat solvent means untouched. Okay. And so you have to remember this vapor pressure is quoted at a specific temperature. Okay, so vapor pressure is quoted at a specific temperature. Right, what is this cursive X with the solvent? This is the mole fraction of the solvent. Okay, so can anyone tell me what the mole fraction means? Okay, so what's in the bottom of the fraction? Mole fraction, mole fraction. So what's at the bottom for a mole fraction? Which would be solute and solvent. That's correct. And since this is the mole fraction of the solvent, what's in the numerator? The solvent. Okay, solvent. Okay. So this is what's called the mole fraction. All right. So in the exam, it's just plug and play, right? Just get the equation and plug it in and chug it out. This is called the mole fraction. Right, there's also another equation. This is the one I'll give you on the exam, but you can also use this equation, the change in the vapor pressure of the solution. Here it's going to be the mole fraction of the solute times the solvent alone. Okay, so you can use this, which is the vapor pressure of the solution, which would be higher or lower. Okay, the resultant vapor pressure would be lower. Or you can use this. And what will this tell you? By how low it went. Okay, the change, the delta. So we can use either this equation or this equation. I think on the exam I'll give you this one, but just realize you can also do the change in the vapor pressure. All right, so let's do this problem here. Calculate the vapor pressure made by dissolving 82.4 grams of urea in 212 mils of water at 45 degrees C. What is the vapor pressure lowering? So we already know the vapor pressure is going to lower. That's one of our 4 colligative properties. right, so if I were to draw this, this looks like this. Okay, so we have individual water. Okay, so we'll use pure water. That's what the deionized or distilled water is. And we have 212 milliliters. And at 45 degrees, what is its vapor temperature? 45 degrees, the vapor temperature is 71.88. So I'll give you that. You don't need to memorize such numbers. Okay? So the vapor pressure here at 45 degrees is 71.88 millimeters of mercury. All right. Now to this 212 milliliters of water. Okay, we're going to add about 82 in green, we're going to add 82.4 grams of urea. Okay, like a little powder. Okay, this would be what would this be? The urea. What do you? What would you imagine it being? The solute or the solvent in this particular case? Definitely, yes, it would be the solute. Okay, and what is water? Okay, solvent. Usually some textbooks like biology or biochem, they'll call water the universal solvent. So yeah. Okay, we're still at 45 degrees. The question is, now we have urea plus the deionized water. What is the vapor pressure going to be? Okay, and we've made a solution. Okay, the new vapor pressure will be lower than 71.88 millimeters of mercury because we added 82.4 grams of urea. Now the question is, what will be the new vapor pressure? Okay, we'll use this equation. Like I say on the exam, it's just plug and play. Okay. So let's first do this equation here. Let's first do the moles of the solvent, which is water. And that is 212 mLs of water. So we'll do the moles of solvent here, water. And the density of water is about 1 gram per ml. That's sort of a back of the backhand or back of the head rough estimation. Because see, this density will help us get us to moles of water. This is the density. Times 1 mole of water is about 18.04 grams of water. Okay, from the periodic table, hydrogen is about 1.01 times the 2 units. Oxygen is about 16.01. We add them together, we get about 18.04 grams. The mils cancel, the grams cancel. And what is this on our calculator? 212 divided by 18.04. 11.752 moles of water, solvent. So this density of water is a rough calculation. You should know it, but I'll give it to you on the exam. So this is the density that helps us get us from milliliters to moles, and I'm getting about 11.75. Let's do 11.75 moles of water. Okay, let's do the moles of solute. We'll do that in green. Moles of solute, and in this case our solute is urea. Right? So let's do moles of solute. Oh, that may be hard to see, so let's just do this here. All right, so we have 82.4 grams of urea times 1 mole of urea is 60.06 grams. 1 mole of urea is 60.06 grams of urea. So 82.4 divided by 60.06, what do you guys get on your calculator when you do that? I'm getting about 1.372. I'm adding some extra decimals just to carry over. All right, let's go ahead and use this equation now. All right, so the vapor pressure of the solution is mole fraction of the solvent. So what's our solvent? Water at 11.752 moles divided by, as Susanna said, the denominator for the fraction will be everything. So that's the moles of solvent, which is this 11.752 moles. Okay, plus the moles of the solute, which is 1.372 moles. Okay, so that's the mole fraction of the solvent times the vapor pressure alone. What's the vapor pressure alone? Okay, without the urea, without anything, the vapor pressure of water alone at 45 degrees is 71.88 millimeters of mercury. All right, so what do we do when we get that? Okay, so make sure you do your calculator correctly. So 71.88 times 11.752 divided by, I'm going to add these two up, 11.752 plus 1.372, 64.34, let's do 64.4. Okay. 64. Let's do, I don't know, 64.37. That's fine. 64.37 millimeters of mercury. Okay, so this is our final answer. So that is the vapor pressure. Remember, vapor pressure, it evaporates, becomes a vapor, and then goes back down. When it goes back down, it exerts a pressure. Okay? That is called vapor pressure.
Did you multiply it times the 71.88?
I did. 71.88 times 11.752 divided by the sum. Just for just for you guys to know, let's utilize this equation, okay, which is the change. Okay, the change, all right. All right, so here we're going to use the same P of solution. Okay, but this equation is going to be the mole fraction of the solute. So what will be the mole fraction of the solute? What goes in the numerator? The moles of the solute, right?
It's going to be 1.37.
Say that again.
I'm sorry. I thought the 1.37 would be in the numerator because that is the solute, unless I wrote this down.
It's the mole fraction of the solvent.
And so in the numerator, it's the mole
Of the solvent.
Solvent on top.
Yes.
Okay, I just wrote it down completely backwards, so this is my bad. I did it.
All right, so if you do it this way, you'll get, what did you get?
I put moles of solute in the numerator instead of solvent.
All right, let's
For
solve
the
it.
mole fraction,
Let's
so-
solve it that way. Let's solve it your way and see what we get. So let's put the moles of solute in the numerator this time. Okay, so here the equation is moles of solvent in the numerator, but we'll do this one, which is moles of solute in the numerator, and solve it. Let's see what we get when we do that. This is what our classmate did. So if we put moles of solute in the numerator, what is that in our numerator? Okay, the 1.372 goes in the numerator. What goes in the denominator? Okay, obviously everything goes in the denominator, the sum, which would be 11.752 moles plus 1.372 moles. Actually, I'm glad you did that because I think it will illustrate a good point for us.
Okay. I mean, I see where you wrote it, and I somehow wrote it down wrong 3 times. So, this is my bad.
And then what's the vapor pressure of the solvent alone? Okay, 71.88. It's okay. You did it right, actually. Okay, we're going to do the same thing, but this time we'll flip it. We'll have moles of solute on the numerator, which becomes the mole fraction of the solute over the whole thing. So doing what Casey did, let's see what we get. 71.88 times 1.372, okay, divided by the sum plus 1.372, getting 7.51 millimeters of mercury. Okay, 7.51 millimeters of mercury. Right, so this is not the right answer, but you're just one step away from the right answer. I hope I can convince you. How is that you're one step from the right answer, Casey? Because it's not the vapor pressure of the solution. Okay, what are you calculating? The change, okay? And what do we know about the vapor pressure? It's going to go down. So you're going to take the 71.88. You're going to take the 71.88 and do what with it? Subtract. Okay, so you'll take delta P solution is going to be the 71.88. We know it lowers. Minus 7.51 millimeters of mercury. So what is that on our calculator? 71.88 minus 7.51, 64.37. Okay, which is the same as you see here. Okay, so you still got the right answer, but what do you need to do next? The additional step? Subtract. Yeah. All right. So I think I'll give you this on the exam, okay? This equation, but if you do what Casey did, which is totally acceptable, just make sure you realize that the vapor pressure goes down. So what do you need to do as an additional step? Subtract. Okay? So good job. Very nice. So you didn't do it wrong. All you need to do is just do the final subtraction. All right. All right, that's very nice. So something like this on the exam. We'll have a review before the exam to go over this again. I think I'll give you this equation, though, on the test. Okay. But if you get, I'll give you this equation. All right, let's do one more vapor pressure lowering problem. Right, here we're going to it's a vapor pressure lowering problem, but it's with methanol and ethanol. Okay, so what's the difference between this and the previous problem? Here, the solute urea was like a powder. Okay, if you ever look at urea, it looks like a white thing that you dissolve, okay, in the water. Here, methanol and ethanol in their natural state are actually what? They're liquids. Okay, so this is not a solute going into a solvent. These are two solvents coming together. Okay. Just as a small quiz, what functional group are methanol and ethanol? What's the functional group? Alcohols. Okay. And will they dissolve? Yes. Why will they dissolve? Because like dissolves like. Okay. So here, unlike the previous problem, it's two liquids coming together. So we have a methanol. We have an ethanol. Okay, so what is the vapor pressure of a methanol-ethanol solution? We're mixing methanol and ethanol, and they'll mix because they're both alcohols and they both like dissolves like. Where the mole fraction of methanol is 0.576 at 25 degrees. Okay, at 25 degrees, the vapor pressure of methanol is 127 millimeters of mercury. So by itself at 25 degrees, by itself, also known as neat, this will have a vapor pressure of 127 millimeters of mercury. And ethanol, let's do this in red, has a vapor pressure of 58.6. 58.6 millimeters of mercury. All right. So the question here is, now we're going to mix them together. Okay, so we're going to mix them together. Okay, we have methanol and ethanol. And the mole fraction here of methanol, we'll do methanol in black ink, is 0.576. Okay, so the mole fraction here is 0.576. Okay, that cursive X is mole fraction. So what do you think our mole fraction of ethanol will be? If the mole fraction of methanol is 0.576, what will be the mole fraction of ethanol? What's our total? 1. So it's going to be 1 minus, see this? 1 minus 0.576. So 1, Royce, good job. Good job. What's 1 minus 0.576? 0.424. 1 minus 0.576. Yeah, 0.424. So now all we got to do is just add them up. Okay, this is kind of like Dalton's law of partial pressure. I don't know if you remember that from Chem 1. Because these are two liquids, these are essentially two solvents coming together, whereas in the previous problem it was a solute mixing in with a solvent. Okay, so these are two combustibles, these are two organics coming together. So we'll just add up the individual vapor pressure contribution. Okay. So methanol is 127 millimeters of mercury. And it has a mole fraction of 0.576. This is for methanol. Ethanol is 58.6 millimeters of mercury. And its mole fraction is 0.424 because it's 1 minus this. And this is the contribution for ethanol. Okay, once we sum them apart, sum these two together, we'll get the sum of the whole thing. So what is this on our calculator? 127 times 0.576 plus 58.6 times 0.424 98. I'll go with 90 as long as there's no objections. 98.0. Yeah, 98.0 millimeters of mercury. Okay, so this will be the vapor pressure of the combined. Why didn't we do the previous way or use that equation? Because these are two liquids. Okay, there really is no solute. These are two solvents coming together. These are two organics. So when you do that, you kind of do Dalton's partial pressure law all the way from Chem 1. All right. So in terms of the test, we'll see something more like this, okay, on the exam. We did a problem involving vapor pressure lowering. Let's do a problem involving the boiling points and freezing points, which we know one will go up, the other will go down. Okay, so let's do a problem involving boiling point and freezing point. All right, I'll give you the equation on the exam. Right, the new boiling point or the new boiling point change will be Kb times lowercase m. Okay, lowercase m. So this lowercase m is molality. So question on the exam, short answer question, just a quiz. What are the units of molality, or how is it defined? Okay, without looking at this, okay. What is molality? So we're going to take this molality m and multiply it by a constant. Okay, the molal boiling point elevation constant. All right, so it's a constant. That's all you need to know, because for water as a solvent, it will be different than benzene as a solvent. So you can see here they have all these different types of constants. Okay, we have the Kf for the freezing points constant, and then the Kb. Okay. The units are going to be degree C over molality. Molality. Okay. Same thing with the constant of freezing. Degree C over molality. So what will the new boiling point be? Will it be higher or lower? This is the change.
Higher.
The new boiling point will be higher. So what do you need to do once you calculate this? What's the new boiling point? You'll add it, right? You'll add it. Okay, once you calculate this, is this the answer? No. What will be like, kind of like Casey's thing with the vapor pressure, what will you do to get the final boiling point? Add. Okay, what about freezing point? Okay, it's the same equation. Okay, m is molality, Kf is the freezing point elevation constant. This should say freezing point, sorry about that, freezing point. Okay, that should say freezing point elevation constant, but it's a freezing point depression constant. So the freezing point depression constant is Kf, and I'll give you this on the exam. I'll give you the constant on the exam. The question here is, what do you do to get your new freezing point? Okay, is this the answer? No, okay. Just like Casey's thing with the vapor pressure problem, what do we need to do to get the new freezing point? subtract to get the new freezing point. All right, so I'll give you the equation on the exam. It's just plug and play. All right, so let's do that problem on page 12 here. Let's see if we can finish this one. All right, let's do a practice problem here, and that's on page 12 of our notes. In the last 10 minutes or so of class. What is the new boiling point and freezing point? 478 grams of ethanol glycol and 3,202 grams of water. The molecular weight of ethylene glycol is 62.07 grams per mole. Okay, so let's draw a picture here. Okay, so we have about 3,202 grams of water. Okay. And what's the boiling point of water? And what's the freezing point of water? 0. Excuse me. To that, roughly 3,000 grams of water. Okay, we're going to add, we are going to add 478 grams of ethylene glycol, right? Okay, 478 grams of ethylene glycol. Okay, our question now is, what is the new boiling point and what is the new freezing point? Okay, by adding 478 grams of this ethylene glycol to this water. Right, so the equation once again is delta TB is equal to KB times molality. Molality. What is molality? Okay, moles of solute over kilograms of solvent. So it's good to ask ourselves, what is the solvent here? Okay. Just automatically, by default, what is our solvent? Water. Okay, water. What is our solvent? Our solvent is water. What is our solute? Ethylene glycol. Okay. So we'll take our 478 grams of ethylene glycol times 1 mole of ethylene glycol is about 62.07 grams. Excuse me. So what's 478 divided by 62.07? Divided by 62.07. About 7.701 moles. Is that what you guys are getting? So 7.701 moles of ethylene glycol. This is our solute, remember. Okay, what is our kilogram of solvent water? Our kilogram of solvent water, we'll just move this decimal 3 to the left. 1, 2, 3. I'm getting about 3.202 kilograms of water. Okay. So this is going to be about 3.202 kilograms. This is going to be about 7.701 moles. And what is this on our calculator? 7.701 divided by 3.202 2.405. Anybody get? Okay, lowercase m. All right, what is KB? I'll give you KB here on the exam, but the boiling point elevation constant for water is going to be 0.52. 0.52. Okay, so we're going to take that and multiply it by 0.52. So let's go ahead and do that. So we have delta TB is equal to 0.52. Now check out the units. Check out the units. Degree C over molal. Okay, times 2.405 molal. Molality cancel. Okay, we're just multiplying it by the constant. And now we'll take that, multiply it by the constant, 1.25 degrees C. All right, this is not the answer though. Okay, on the exam, what will be our answer? What will be our new boiling point? So new boiling point after the addition of 478 grams of ethylene glycol to 3,000 grams of water, what will it be? Will it be 1.25 degrees C? I know a lot of students will write this on the exam. But what will the new boiling point be? Yes, it will be 101.25 degrees C. Okay, so this is the answer. So adding ethylene glycol will raise the boiling point to 101.25 degrees. And this is like antifreeze, or not antifreeze, yeah, kind of like antifreeze, okay? Actually, the antifreeze thing is more for the freezing point, so let's quickly calculate that in our last 3 minutes or so, okay? So on the exam, it's just plug and play. Okay, what did we solve for the molality? 2.405 molal. Okay, what is K of F for water? All right, K of F for water is 1.86 degrees C over M. Delta TF, the change in the freezing point, the molal cancel. So 1.86, this is a constant, times 2.405, 4.47 degrees C. Okay, is this the answer you'll put on the exam? So what will be our new freezing point be? The ethylene glycol is kind of like antifreeze. So what will our new freezing point be? We don't want to put this on the exam, but what will it be? Correct, very good. Negative 4.47 degrees C. This is the answer.
So you always subtract it from...
If you're calculating the freezing point, yes. And if you're calculating the boiling point, you'll add it. Because what are the colligative properties? Boiling point elevation and freezing point what? Depression. Yeah. So a lot of students in previous years will just calculate the change. And no, the new boiling point is not 1.25 degrees. The boiling point, if your solvent is water, for water, because the solvent is water here in this problem, the boiling point is 100, so it will go up by 101.25. This is how antifreeze works. So instead of freezing at 0 degrees, it's going to freeze at minus 4.47. I think they put it in your cars or something. Okay, so yeah, ethylene glycol is antifreeze. So let me give you some announcements before I end class here, the last minute. I think I